So the three tests which we just discussed, they're only feasible if your sample is saturated. So the important point in triaxial testing is you need to use a saturated sample. So cases where your sample is come up from the ground, even if you have collected a sample from below water table, when it comes to above the ground, it's transported to the lab. So certain amount of loss in water is expected, so the degree of saturation can go down. Now the thing is, what do you do when you need to saturate the sample? Okay, you can do two things. First is you jack up your cell pressure. So I have the sample already in. I have still not started with triaxial test, but my cell is all filled with water. Okay, it's all filled with water, and it's ready. But the water is still not under pressure. It's still just there. So the first thing is, I know the sample is not saturated. So those kind of things, I'm presuming that it is known to us. Although there are procedures for this, even before putting the sample on, I will not be able to discuss all this. But if it is known that the sample is saturated, I have first choice is to I apply a lot of pressure, cell pressure through here. Keep all my valves closed. I can, however, keep this PPT valve open because it's just a gauge. I'm not allowing any water to escape, right? So I can increase the cell pressure by a certain amount. See the pore pressure gauge reading, and the screwing it is by increasing this cell pressure, knowing that at about 200 or kPa or so, the air starts to get dissolved within. You would see that many samples, the air bubble gets still trapped here and there, and increasing this cell pressure by significant amount is not even feasible for the test, because this cell is limited to 1000 kPa working pressure. So this working pressure is usually 1000 kPa. Equipment itself, which is used to pressurize this, can have a working pressure of about 800 kPa. So you have a limit to how much you can go. Okay, 800 kPa is if I'm using air. So I use air as pressure. Of course, let me look at the other procedure. The most handy equation to confirm what is the level of saturation achieved is Skempton's pore pressure equation, which we have just introduced a while earlier. Right, so all sigma 1 and sigma 3 are the changes. Please remember, these are all deltas. These are the changes. So do recall, we are doing test on all saturated samples. Samples which are saturated. To confirm that the samples are saturated, I need to check a certain V coefficient. That's the most important to know whether my sample is saturated. So coming back to the first equation over there, when I just apply the cell pressure in the triaxial chamber, okay, we have just seen when only cell pressure is applied, this term over here in the Skempton's equation turns out to be 0, because both sigma A, delta sigma 1 and delta sigma 3 are same. They have the same value. So I have delta U equals to B times delta sigma 3. Now U equals to B times delta sigma 3. So when I apply a certain amount of cell pressure, so I started from cell pressure of 0 and I moved to a certain value. Now I'm going to throw in some numbers just to help, increase this to a value of say 50 kPa. That's the example I would normally take because it helps in calculation. And my delta U, so that's the change in sigma 3 or cell pressure. My delta U initially was 0. Maybe it jacked up to, let's call it, say, give a number, say 40 kPa. So that's the delta U. So I get my B value as 40 minus 0 over 50 minus 0. So that's 0.8. Okay, usually I would prefer B value of as close as to 1, so that I'm this ensures that the sample is saturated, but a B value of close to 0.95 is also accepted. Okay, I can also make say that this value, if it's acceptable, I can perform the test. Now so in this case, of course, let me erase this out because these are the values which I used just to explain. I need to get a value which is much higher. I need a much significantly higher than 0.8. Okay, for this I have to now use a term called back pressure. This is important. Ground to this. How would I think of ways I can saturate the sample? So if I just zap this again, I'm going to have zapped it few times. I'll just zap again and bring it down. That's my figure. Back again. Okay. Use a term called back pressure. Meaning the same thing, but over here now I don't have a tube. I close this tubing, right? So the tubing which is there, even if I have even if the tubing was there, I can't remove the tubing within the test. Okay, I just close this valve. There's no more escape, and the water which I allow to push in, I push it under pressure. So under a higher pressure, significant, can be up to few hundreds of kilopascal. Now if this water pressure is high enough, I have to ensure that the pressure which is outside in the chamber, that should also be high, and it should be higher than the water pressure. So pressure in the chamber should be higher than the pressure in the soil sample, right? Usually we keep a lag of about 5 or maybe 10 kilopascal, not significantly large, because the pressure in the chamber represents your total stress, the pressure in the water represents your pore pressure. So the difference between the two should be small, so that you don't change the effective stress during the saturation stage. Okay, so for the back pressure to occur, what I will do is I will apply. So if I just use the same figure to when I'm going to push this water in. I'm pushing the water in, that's here, and I have also increased the cell pressure. So what I do is my cell pressure goes up first, okay, and then as a follow-up, I increase the pressure within the soil sample. Okay, now what you will notice is that because you have a higher pressure, so coming in within the sample, this higher pressure would help dissolve the air. Okay. A pressure of something like over 150 or 200 kilopascal or higher, it has been seen that it helps to dissolve the air. So coming back to those numbers again, remember we had a number like over here my sigma value was 50 because I started from 0 and I went to 50, and my pore pressure was 40 because I started from 0 and it went to 40. And my pore water pressure increased from 40 to the value of the back pressure. Now the value of back pressure is under your control. Always remember, back pressure is under your control. So if I apply cell pressure of 200, I'll probably put back pressure of say 190. Let's fix it as 190. So this value here is 190 kPa. Right, it's fixed. Then once this is done, I then allow nature to do its job. The water will help dissolve some of the air. Okay, it'll reduce the size of the air bubble, etc., etc., and perhaps increase the degree of saturation to some extent. Now once I have left it for a few hours, I will then come back to this figure again. Okay, I think I'll zap this figure back again, or let me draw this figure. I think it's easy to draw. I like doing this. This is draw. That's my sample, right? And this was the opening below the sample, from where so that's the opening below the sample, from where I pushed in back pressure, and your cell was filled with water. Under pressure, that's 200 kPa, and back pressure was 190 kPa. Now once you have allowed nature to do its job, you will close this valve. Let's close this valve. So 190 is locked inside. Okay, so U equals to 190 is locked. My outside cell pressure is 200, which I have applied. The second procedure for saturating the sample is by using back pressure. So we have just seen, how back pressure in terms of the quantity, but let's physically look at how do you apply back pressure on a true cell like this over here. So for back pressure, what I've done is the bottom drainage which we had, the same valve I'm going to use for back pressure. So I've written back over here. Now you got an extra label over here which says back. So the same valve is now bottom drainage, and back pressure is the same valve. Okay, so I have this. So what I do is that I keep this valve, I open this valve and apply a larger amount of pressure from within the sample to within the sample. So I apply pressure from here. It goes inside, and it is right under on the pedestal. So it is one of the holes which is there on the pedestal. So I keep this connected to the outside world using this valve over here. Okay, now one thing over here is in the previous case I applied pressure from the outside and then prayed to God that the pressure which is generated inside the sample helps to dissolve the air. But this time I have applied pressure to inside the sample. Right, the pressure is here inside the sample. One precaution which I have to see is, if the pressure in the sample is on the higher side, higher than the cell pressure, then the sample is likely going to be burst. It's going to be a small bomb. It will just explode. So I need to have the cell pressure to be higher than the pressure which is inside the samples to maintain a slightly positive effective stress. Okay, we have just discussed this. How do we do that? So the way out is, I keep my cell pressure, I increase the cell pressure. Okay, keep it at a slightly higher value compared to the back pressure. So one way out is, my cell pressure is at a certain value, which is maybe about 5 or 10 kPa higher than this. So one way out is, I open these two valves together so that the chance of sample getting exploded is minimum. You will find that this opening is a trick. If I just lose a fraction of a second, I may end up destroying the sample, because this fellow over here can go faster if my opening of this valve is not synchronized with the other valve. The correct way of doing it is, I the cell pressure, I increase the cell pressure first. Okay, and then once the cell pressure gets increased, then I increase the back pressure. Reason is, by increasing the cell pressure first, I don't disturb the sample. My loading in the sample is still elastic. There is no consolidation of the sample ongoing because the valves which are for consolidation, drainage, top and bottom are all closed. So no consolidation occurs. So my sample is not disturbed when I apply cell pressure alone. Right? Now I apply back pressure or from the bottom, which is about 5 or 10 kPa less than the cell pressure. So I then once this is done, I allow nature to do its job. It can take about a day, for some impermeable soils even more than a day for this the whole thing to stabilize. That given some examples that the cell pressure, okay, I have increased from 50 to 200 kPa. That's 200 over here. Now 200 is within the chamber, and the back pressure I have increased to 190. So the pore pressure within the sample was 40 kPa, but now this 190 goes and hits the sample, so bombards the sample. So the pressure within the sample, pore pressure within the sample is going to increase and reach a value of 190. So once it reaches a value of 190, it's going to stabilize with this, and this 190 would be within the sample. Remember, so 190 goes from the bottom, and within the sample I can read 190 from this pore pressure reading. So once this PPT reading gives me 190, I can be assured that whatever the pressure, back pressure I've applied from outside, the same is within the throughout the sample. You have the same value. Now there is one term which we used earlier, is the short circuit. Remember we said both the holes are at the bottom. So if I apply 190, it's quite likely that the pore pressure transducer will read 190 immediately. So it may give you a false feeling that the sample, the pore pressure within the sample has stabilized and there is no more change. Okay, no more change occurring. But during this process, because you may find the water is still going in, because the water goes on inside, right, from this back pressure line. If water is still going in, you can expect that some amount of air voids are still being filled with water. So not necessarily the gauge gives you the correct reading in those cases. You may have a situation where instead of this top drainage, I can connect a gauge over here. So the gauge is now connected to top of the sample. I can then read out what is my pore pressure reading at top of the sample. Remember, I'm just using this as a dual purpose. Instead of top drainage, I use it as a pore pressure reading. I connect a PPT to it, right? So once the sample, the stabilized to a new back pressure and cell pressure value, I would close this back pressure, close the cell pressure for, and then jack it up. Okay, we have just seen that the pore pressure we increase is now at 190. The cell pressure is at 200, and I need to check my B coefficient again. So all my valves closed except for the PPT valve, which is open. Okay, it just gives me a reading. What I'll do is I'll the cell pressure, which is now 200, I will increase this to 250. Okay, that's what has been. So it's increased to 250. So 250 over here waiting to be hit. I open this valve. So 250 is now within this chamber. Okay. Previously the pore pressure within the chamber was 190. That was the reading given. But now from 190, this reading tells me it's say let's say throw in some number 235. Let's go to the whiteboard again, see if this 235, what reading do I get. So we have seen that pore pressure, it goes from 190, it goes to 235 because the cell pressure increased to 250. Let's look at the change. change in cell pressure, that's delta sigma. I get 250 minus 200, I get a reading of 50. And the change in pore pressure is 235 minus 195, I get a value of 45. This gives me a B coefficient of 0.9. So in other words, this I need to go do a next set of back pressure saturation. I have to go for my second stage of back pressure. Let's see how it looks like in this setup. Okay, now all my valves I've got to close, so my valves are closed. My cell pressure I have increased from 250 to 350, so 350 is waiting out over here. I open this out, now 350 is within the sample. That's my back pressure, right? So for the back pressure, I had my desired value, which I have now applied a pressure, water pressure over here, is 345, which is just about 5 kPa less than over here. Okay, I open this out. So 345 within the sample, 350 outside the sample. So the effective stress right now is just about 5 kPa. It's going to make it's not going to harm the sample significantly, because it's not going to disturb the sample. This value 5 kPa which I have chosen is significantly less than the final consolidation pressure which I will desire at the end of stage 1 of triaxial.